So there's nothing really that I want to review or go over from yesterday other than to remind you that all of those details that we talked about, whether it's specific wavelengths of any of those 7 groups of electromagnetic radiation, and after today's lesson you'll be able to tell me about frequencies of those as well. So I'll pause there. I guess what I'm saying is if I give you a wavelength, you should be able to identify the name of the type of electromagnetic radiation we're talking about. And if I gave you maybe 4 different types of electromagnetic radiation, you should be able to put them in order from shortest wavelength to longest wavelength, or vice versa. Short wavelength, of course, is a lot of energy. So those are things like gamma radiation, which has the shortest wavelength because it has the most energy, going all the way to radio waves, which have a very long wavelength, so not a lot of energy. You need to be able to tell me how each of them are produced, what each of them are used for, and that's it in a nutshell. Today what we're going to do is talk about electromagnetic radiation behaving like a wave. And we'll often say that in science, that light, or EMR in general, behaves like a wave. Or we'll say it behaves like a particle. And again, even though this is not really part of this lesson, I want to talk to you for a few minutes about the difference between transferring energy using a particle and transferring energy using waves, because they're really, really different ideas. And the better you understand the difference between wave energy and particle energy, the better off you'll be when we talk about EMR as a wave or EMR as a particle. If I wanted to transfer energy across the room, let's just say you were on the other side of the room, and I wanted to transfer energy to you, but I wanted to do it through a wave. I could design a very ingenious kind of way to do that. I would close the door. We wouldn't be in here. I'd close the door. We'd seal all the openings in the doors and anything else that stuff could leak out of. And then I would come in from the ceiling and I would fill the room with Jell-O. I'd pour Jell-O before it's set into the room so that maybe there's about 3 feet of Jell-O, about 1 meter of Jell-O deep. And then we could somehow cool the room to get Jell-O in the room. And then what you have to imagine is that we've got a sheet of plywood that's on top of the Jell-O on one side of the room and a sheet of plywood that's on top of the Jell-O on the other side of the room. And because the plywood is spread out over a large surface area, it'll sit on the Jell-O. It's not really floating, it's just supported by the Jell-O. And I lower myself down from the ceiling until I'm sitting on top of one sheet of plywood, and you lower yourself from the ceiling until you're sitting on the other piece of plywood. And the idea is I want to transfer energy from me to you. And if I use a wave idea, all I have to do is just kind of bounce up and down on my sheet of plywood. And that's going to cause a disturbance in that medium. The Jell-O is called the medium, the substance that the wave travels through. I'm going to cause a disturbance, and because Jell-O jiggles, that disturbance is going to be carried through all of the jiggling or vibrating or oscillating of the Jell-O from where I started this phenomenon over to you. And sooner or later, even though you're just sitting there very, very still, the plywood and you on top of it is going to start to move. So what I've done is I've transferred energy through the use of a wave, and it requires some medium between the 2 points that's going to vibrate or oscillate, or in the case of Jell-O, jiggle. If I wanted to transfer energy to you through a particle, then I could grab a handful of Jell-O and throw it at you. And the Jell-O would move through space from one place to the other, and it might smack you in the head, and I've transferred energy to you. So there's a huge difference here between wave energy and particle energy, and it has to do with how they move from one place to another. We're going to be concentrating on the wave model today. This is not in your notes, what I'm showing you here. I used to include it in the notes, but it's not necessary for you to write it down. But I do think it's valuable for me to talk about briefly what we call classical models. I'm thinking here 1600s, 1700s, 1800s, 200-300 years ago, 400 years ago, and what the scientists of that time thought about light. You need to be aware that people like Isaac Newton or Thomas Young or Christian Huygens these scientists of that time, they were not aware of radio waves or microwaves or any of these other forms of EMR, but they were aware of light, visible light. And Isaac Newton has a really, really good argument for assuming light is a particle. Because in order for it to be a wave, there has to be some medium, some substance that does the vibrating to transfer the energy. But we know, and they knew, suspected anyway, that between the sun and the earth is a vacuum. There's a vacuum of space. There's nothing there. And yet light can go from the sun to where we are on the earth. So Isaac Newton would look at a guy like Thomas Young and say, I think you're insane. How can you say that light is a wave when there's nothing between the sun and the earth that can wave? And Newton's got a point. But Huygens and Thomas Young did experiments, and we will talk in detail about these experiments later in this unit, where it's undeniable that light travels through light. It interferes. And you talk about interference, just a thin veneer of it in Physics 20. But when you have one wave that passes through another wave, what happens is if this is a ripple on a wave traveling this way, and this is a ripple traveling this way, what they do is they overlap and create a big wave, and then they continue on their way. And particles don't do that. If particles did that, well, it would be a weird world. We couldn't play baseball because you'd swing the bat and the ball would just go through each other. Nothing would operate the way we're accustomed to it operating. So the fact of the matter is, Young had strong evidence to show that light is a wave. And what he does is he looks over at Newton and says, well, you're crazy. It has to be a wave because look at the evidence. And in the end, you have this kind of paradox. Paradox is something that seems to be impossible. Okay? Because and this is the way I like to think of it, we've kind of pigeonholed ourselves with the language that we've created in science to assume that something is a wave or a particle. And I guess what I'm saying is light sometimes behaves like a wave, and it sometimes behaves like a particle. I haven't given you modern evidence for why we believe it's a particle. We believe light is a wave because it interferes. That's what we believe today. We believe light is a particle today because of certain things that light does that Newton didn't know about. So this is why it's called wave-particle duality. So the question is, if this is a laser, if light consists of a bunch of little particles of light energy traveling, or light consists of a wave, those are two entirely different things. And this is the answer to the question. There is no answer. Now, a quantum physicist might say it's a particle. Okay? And they have ways to kind of explain wave-like behavior by talking about particles. But at this level, we say, you know what? Sometimes it's a wave and sometimes it's a particle. It's kind of a spooky thing. So what we're concentrating on today is the wave model. And the wave model, I guess I can tell you right on the outset of this, is called the electromagnetic wave model because it explains light and all other forms of EMR as being a wave with no physical medium. Which right away is a little bit troublesome in the brain. Like you're saying it's a wave, and a wave is transferring energy because something vibrates, but you're telling me there's nothing there to vibrate. That's exactly what I'm saying. Something is vibrating, but it's not physical, which is really weird because everything you know is physical, right? I'm not saying it's imaginary, by the way. I'm saying it's real, but it just doesn't have substance to it. So James Clerk Maxwell in the mid to late 1800s, he was a Scottish physicist, he looked on all of the work that physicists prior to him had done with electricity and magnetism, and he had an idea. And he published these two principles. He calls them the principles of electromagnetism, and they're true. We've got lots of evidence for them to be true, even coming up on 250 years, over 250 years from this point, we still believe them to be true. That's not to say that we might not find exceptions to them later. I mean, science is never really finished. the first principle of electromagnetism that he published says, if you have a changing electric field, the key word is changing here, if you have a changing electric field, it will produce a changing magnetic field. So what's a changing electric field? Well, if you just had a charged particle sitting there in space, that's not a changing electric field. It has to be in motion. And the reason it has to be in motion is the following. This is a little hard to follow, and I don't really know that I need to explain it this way, but I feel as though I want to. If we had a charged particle, it's a charge, it's the source of an electric field, and let's just say for a minute that it happens to be a positively charged object. So the electric field from the last unit is a radial electric field that radiates away from the charge. And I have a point in space here. Maybe it's where I'm sitting there observing, or it's just some point in space. And I told you that a changing electric field occurs if you have a charged particle moving. Now, there's going to be a little bit more to that in a second, but if you look at the strength of the electric field at that point P right now, there's an electric field there, right? I hope you're not saying, well, the field lines don't go that far. They extend out to infinity. But is the electric field at this point, right now in this picture, the same as the electric field here? So I've got the charged particle that's moving through space, and it's passing me now. It's in a different location. And even though the electric field surrounding that source is the same, it has a different value at this point in space that I'm talking about. It's stronger now because I happen to be closer to it. Now, there's a little bit more to that. That's a little bit of a watered-down explanation. It turns out that the particle has to be accelerating. Okay? But we'll get to that in a bit. So that's the first principle of electromagnetism. His second principle, all a principle is a statement that we believe to be true. His second principle says the opposite. If you have a changing magnetic field, you'll produce a changing electric field. So on the one hand, you have a changing electric field that will create automatically in nature a changing magnetic field. And he's saying, guess what? A changing magnetic field creates a changing electric field. I hope it's clear that the magnetic field that's changing because of the first principle is a changing magnetic field which can produce a changing electric field, which is what the second principle says, and that can produce a changing magnetic field which can produce a changing electric field, et cetera, et cetera, et cetera. And he recognized this, right? He's not a fool. He recognized that if you can create a changing electric field, you will automatically produce a changing magnetic field. Well, you won't, the electric field will. That will produce a changing electric field which goes on and on and on forever. And what he did was he did mathematics with this. I'll show you the equations he worked with later. I know it probably sounds as though I'm just kind of making this up and saying, well, he did math with these statements. There are actual equations. So he did mathematics based on these principles that he created, based on the physics that his fellow scientists before him had done. And he came up with this model of EMR. This is called electromagnetic radiation or electromagnetic waves. He said the only thing based on the equations that these fields mutually creating each other could produce would be something we can visualize that looks like this. Now, in your note package, it says, we will complete the diagram. It shouldn't say that. I've got the diagram completed for you. It's a very difficult thing to understand. So first of all, what's waving? You know what is waving is not jello, because it's not a jello wave. It's not air, because it's not a sound wave. It's not water, because it's not a water wave. It's electric and magnetic fields. And a field is a mathematical idea that explains forces. So I hope I made this diagram myself because some of the diagrams I've seen in textbooks, I don't think they have that 3D that pops out and shows you what's going on. I hope that if I gave you some red construction paper and some blue construction paper and some scissors and tape, you could make this thing. What the red flaps are flaps that are oriented vertically. What the blue flaps are flaps that are going out of the board towards you or into the board away from you. So one of the things you will notice is that the angle between the electric field and the magnetic field is always 90 degrees. Now keep something in mind. This is just an idea at this point. Maxwell could probably be described more as a mathematician or a theoretical physicist as opposed to a scientist who does experiments. This is just what the equations are telling him. They are telling him that if you take an electron, let's say, and you shake it up and down, then that will set in motion this chain of events. By shaking it up and down, you will create an electric field that increases in value, then decreases and increases in the opposite direction, and continues this process. You do not have to continually shake this. Once you start the process, this wave travels out through space. But because this changing electric field, according to his theory, produces a changing magnetic field, as the electric field is increasing, the magnetic field is increasing. And then as the electric field decreases towards zero, the magnetic field decreases towards zero. Then as the electric field increases in the opposite direction, the magnetic field increases in the opposite direction. And I would say he was doing this as an academic pursuit, but more of a thing of interest. He took some ideas, he played around with it, he saw what the prediction would be, and it predicted that you would get this phenomenon. Other predictions of his, and some of these are pretty weird, other predictions of his is that this wave should move at the speed of light. Now, he didn't necessarily know what the speed of light was, but he took his formulas and he did calculations with them and he did the math with them, and it's really bizarre. I'll show you the equations in a bit. These very complicated equations boil down to all these waves have to travel at 3.00 times 10 to the 8 meters per second. Now that happens to be the speed of light. So once the speed of light was determined, the obvious conclusion is, well, maybe this stuff that Maxwell is hypothesizing, maybe that's what light is. And it is, by the way. I'm going to show this to you because I think it might be beneficial for you to see what this looks like. And it crashed. So what you're looking at is an electromagnetic wave traveling kind of out of the board towards you. And for the most part, their electric field on this is blue and their magnetic field is red. They're just arbitrary colors. The electric field is, for the most part, oscillating to the left and the right. The magnetic field, on the other hand, is oscillating vertically up and down. And it's that charge that's the blue dot that's being accelerated back and forth between the two ends of whatever that thing is. It's a spark gap, it's called, that's producing that field or those mutual fields. I might have to use a mouse here. If I adjust it so that we're looking almost in the same orientation as the electric field is oscillating, you can't see the electric field. You can only notice the magnetic field oscillating up and down. So This diagram that I'm showing you here is a snapshot in time. These waves are traveling from left to right in this diagram. Now they're also traveling outward in space in all directions. So going back to what I said about if light is a wave, what's waving, it's nothing physical. What's waving is an electric field and a magnetic field, which is a very wild idea because a field is just an invention of the human mind. There's nothing there physically. Electromagnetic radiation will always be produced when there is an accelerating charge. So now you have to add this to a running list of things you know about fields. If you had, let's say, an electron sitting in space, then there is a gravitational field because it has mass. There is an electric field because it has charge. If you have an electron that's moving at a constant speed, then you will have a gravitational field, an electric field, and a magnetic field. Now what I'm telling you is if you have an electron that's accelerating, you're going to have these three fields and you're going to have electromagnetic radiation produced. Now stop and think for a second here. So this is no EMR, according to Maxwell. And I hate to say it that way because his theories are right. I don't mean to imply, oh, well, we're going to learn that they're wrong. According to Maxwell's explanation, though, there's no EMR produced there, and that is a fact. If you have an electron that is accelerating, this means there's an acceleration that's not equal to zero. Then, yes, you still have those three other fields, but that's not the point of this lesson or of the topic. What you're going to do is produce EMR. Now, I take you back in time to Friday. How are radio waves, which are a type of EMR, produced? They're produced by electrons oscillating in a linear antenna. In order to get an electron to speed up, slow down, stop, change direction, speed up, slow down, stop, change direction, in order to get an electron to oscillate, it has to experience acceleration. There's your accelerating charge. I told you that microwave radiation is produced by electrons trapped in a circular orbit due to a magnetic field. Well, circular motion is a type of acceleration. It's a changing velocity. I told you that for infrared, visible, and ultraviolet radiation, you have electrons that lose energy in an atom. It's a little bit different here, but I can basically just tell you that when you have a charge losing energy, it must undergo some type of acceleration. Okay? It's not kinetic energy that's being lost, so it gets a little bit iffy. How are X-rays produced? By high-speed electrons suddenly being stopped by a metal target. Well, that's a type of acceleration. It's a negative acceleration. And I'll stop there because I can't really explain gamma radiation in terms of accelerating charge. It's the exception. If the acceleration of the charge is periodic, like me dipping my foot in and out of the water at a regular rate of 5 times per second. When I dip my foot in and out of the water at a rate of 5 times per second, I produce a water wave with a frequency of 5 hertz. If I shake an electron back and forth 1,000,000 times per second, I'm going to generate electromagnetic radiation with a frequency of 1,000,000 hertz. So whatever the frequency of the periodic motion is, that's the frequency of the EMR. Excuse me. And it turns out he predicts, and we don't need to worry about the finer details of this, but there's 2 types of waves in terms of vibrations. One is called transverse, one is called longitudinal. How many of you, first of all, remember those words? How many of you remember what they mean? even fewer. Transverse is when the medium oscillates, say, up and down, and the energy moves away in a perpendicular direction. Longitudinal is, and we will review these when we need to later on in the unit, officially in a lesson. Longitudinal is when the medium oscillates back and forth, pushing the energy in the same direction as the oscillation. So here are his equations. I'm just showing them to you, and I never really decide if I'm going to show them to people until we get to this point in the lesson, but let me show them to you. These have mathematical symbols in them that you don't even understand. If you take calculus and I were to show you some of this stuff, you would recognize some of the stuff, but they're quite complicated equations. These are his equations that he was working with, and I call them Maxwell's equations, but really Ampere came up with one, Gauss came up with a couple. There's called the Maxwell-Faraday equation. There's something called the differential form and an integral form. Man, it's just math. And it turns out that if you take all those equations and use algebra with them, it reduces to the following statement. It reduces to the speed with which this stuff spreads out through space is equal to this. On the bottom of your screen, there's V equals the square root of 4 pi k. That k, by the way, is Coulomb's constant. Over mu sub 0, and mu sub 0 is called the permittivity of a vacuum. And when you put them into, you could calculate it yourself, you get the speed of light, which is really a surprising result. Out of all of that mess, you get the speed of light. So I'm going to pause there, and we'll just take a look at this diagram again. One of the things I want to point out to you before we move on is that the electric field at any point in time and the magnetic field at that same point in time and the direction that the wave is moving, which is your time axis, are all three perpendicular to each other. So, for example, if the electric field is down towards the floor at some point and the magnetic field is towards the right of the room at some point, the wave must be traveling towards the back of the room or the front of the room. All three, both of my legs right now and my right arm, are all perpendicular to each other. Any questions or comments about what this is saying about what EMR is? Okay, well, good stuff, Maxwell, but anybody can say anything. Is it actually true? And it turns out it is. We cannot, at this level, do a really valid experiment to show the evidence of EMR, but I've come up with something which I think will help a little bit. A short time, within about 2 years of Maxwell coming up with this idea, Heinrich Hertz, the same person who we've named the Hertz unit after, provided evidence to show that it's true. So if I had to say what's important right now, it's important that you understand what that electromagnetic wave picture is telling you, and that Maxwell proposed it, and that Hertz validated it. Hertz did experiments to prove it. Basically, again, Hertz recognizes that a changing electric field is an accelerating charge. So that's how we can initiate the chain of events. And what he did is he used an induction coil and a loop of wire. And I noticed on your handout there's some weird lines coming off at angles on this, but they're not important. I don't know, can't get rid of them on your copy. What is an induction coil? Well, this is an induction coil right here. And if we had more time, I could explain to you, and I might do it tomorrow or at the next seminar. I might explain to you how this works. But basically, there's an electromagnet in it. There's an electromagnet which, when I apply a voltage to these terminals, the electromagnet turns on and attracts a part of the circuit which breaks the circuit and turns the voltage off. But when the voltage is off, the electromagnet is no longer operable, and that piece that it pulled over is on a spring which pulls it back and closes the circuit, which turns the voltage back on, which turns the electromagnet back on, which opens the circuit. Opens the circuit means disconnects it. And it just keeps going back and forth. And it turns out that action of making a connection and breaking a connection produces a spark. Some of you, I'm sure, have noticed if you plug something into the wall, sometimes you'll see a spark just as the prongs are going into the outlet, and sometimes you see it, sometimes you'll hear it when you pull it out. I don't know exactly why that is. I think it's because there's a voltage there, and you're creating a very, very small gap, and that voltage is strong enough with a small gap to create a great enough electric field that pulls the electrons across. Just like if I get too close to the Van de Graaff, there's a spark. That's basically, I think, what's happening. So this is all connected to these two pieces of copper wire up here, which means when I turn this on, it sparks. Now, you're getting a continuous sparking back and forth, and I'm sure you can hear the sparking, but I don't know, if you're really close, you can hear the vibration down here where the spring and the lever continually opens and closes, and I can adjust this. If I tighten it so the spring is really tight, well, I guess I'm loosening the spring. Anyway, if I change the tension in the spring, it will vibrate at a different rate. It will open and close more rapidly, as it is in this case. So I'm getting a higher frequency spark. So just to break for a second here, this is an accelerating charge. These electrons are jumping back and forth across this gap in here. This gap in here is where the electrons are jumping back and forth. So it's producing a changing electric field, which according to Maxwell produces, at the same time as it moves through space, a changing magnetic field, which produces a changing electric field, etc. And what's happening here in his experiment, I'll give it to you in words first, is whenever the induction coil produced a spark, which is this, whenever this was sparking, the coil that you can think of as a detector, which is just a loop of wire, it's the diagram on the left side of your notes, that would spark, even though it's not connected to anything. So visually, this is what's going on. You've got this induction coil, and you have a loop of wire with a gap in it. Now I've got my diagram connected to a tuner. This is just an antenna. This loop of wire is an antenna, and this loop of wire is the transmitter. I've got that this antenna is connected to a tuner because of the demonstration I'm going to show you. But even if it's not, it would spark on its own if I had the right equipment to show it to you. Okay? I can't show it to you, so I've attached a tuner to the coil of wire so we can hear it. Okay, and I will show you that in a second. But looking up here, when there's a short spark at the spark gap, a very short time later there is a spark received at the loop of wire. So something traveled through space from the induction coil to the antenna. If that's continually sparking, then the antenna will continually be sparking. And I hope you see a similarity here to what I told you about how radios work. This is the same thing. Okay? In fact, the thing that I'm going to use that has an antenna and a tuner is a stereo. I don't know if I can get this going. Now, when you tune a radio to a random channel in which there's no broadcasting on that band, it's making noise. And the only reason this is making noise is because something is causing the electrons to move around in the antenna. If I disconnect the antenna, you wouldn't hear anything. You might hear something because of electrons moving in the actual device. But so whenever I get a spark happening, if Maxwell is right, I get a spark happening over here, it will produce EMR, which will travel through space, and it will bang into this antenna, causing electrons in it to move, and we will hear something different. Now, long before the internet was around and we all had satellite radio and all that stuff, everybody in my Physics 30 classes, it would make sense to them because I'd say, it's like if you're at a drive-in and you're listening to a radio and you've got the movie tuned into the radio, but there's a lightning strike someplace, your radio goes all haywire. And everybody go, yeah, I know what you mean. You guys don't know what that means because you don't listen to that kind of radio anymore, really. I mean, you might. I would use the analogy of, I remember being a child watching TV, and my mom would be making something in the kitchen, and she'd use her electric mixer, which had an electric motor with electrons moving around, and the TV would get all scrambly. But that doesn't make any sense to you, does it? I don't think. Have you ever experienced that? Probably not. So let me turn this on. We can hear it here. And I can even adjust the frequency here. And it's replicated over here. Now you could make the argument, I'm just going to turn this off so I don't have to shout. You could make the argument that something is bumping into the air and the air and the air and the air. But when Hertz did this experiment, he did it through a vacuum. So there was nothing physically between them. And the bottom line is, whatever the frequency of the vibration here is, that's going to be the frequency that you hear over on the left-hand side. Just trying to get a couple of sparks per second. So it's mimicking it. Whatever's happening here is happening there. Sorry, there we go. And this is basically, I'm going to try something else now. I'm going to move these really close. This is basically the idea behind the old telegraph that you would see in old movies. So I close the switch here, it produces something over there. You would just have to connect this antenna not to a speaker, but to an electromagnet that would move every time I close the switch here, or open the switch, and then it would move up and down. Anyway, I hope that gives you an idea of what we're talking about here. It's very far removed from the experiment that Hertz performed, obviously, because he didn't have an antenna. There's evidence of EMR because the one spark produces the next spark. By the way, this is a picture of some of the original equipment that he manufactured and used. His induction coil is not shown here. You would hook the induction coil to these two spheres, which would build up a huge charge, and every time the voltage changed, there would be a little spark right in this gap, and then a distance away, you would see a spark there. One of the things he learned, and I'm sure I passed it by, I'll show it to you here. If you do calculations using the distance between the spark that starts and the spark that's created and the time delay, you discover that something is moving from one to the other at the speed of light. So Maxwell's right. Okay. All right, so light is a wave. Well, it's a wave some of the time. When these waves were first discovered, I don't know if this is in your notes because I changed your note package this semester. He was producing radio waves. This was the precursor to radio, what they would call wireless at the time because you didn't need wire. And for a long time, radio waves were called Hertzian waves, named after Hertz. So, what are we going to do with this? Well, in terms of formulas, If electromagnetic radiation is a wave, then you can use these two equations or formulas on the left-hand side. The first formula, do you recognize it? V equals F lambda from Physics 20. This is called the universal wave equation, and now I can say to you finally, it's called the universal wave equation because it works for any waves. Mechanical waves, which you study in Physics 20, are waves that have a physical substance oscillating, and that equation works for them. Electromagnetic waves, which we're studying now, has no physical substance oscillating, but the fields in that wave still have a frequency and a wavelength. The period of a wave is the reciprocal of the frequency. Should maybe just go through something briefly here. This is the period. It's measured in seconds. This is the frequency, measured in per second. This is the actual unit of frequency, per second. So when you say, I have a frequency of 740,000, you're saying something is vibrating 740,000 times per second. Except we abbreviate that as the hertz. This is the wavelength. These are things that I believe you already know, but I would hate to leave anybody in the dust here because I just failed to review it. Wavelength is the distance from crest to crest of a mechanical wave. And for an electromagnetic wave, okay, it's a bit of an optical illusion trying to draw that. The wavelength is the distance from crest to crest of one component, so that could be the wavelength, or the other component, that could be the wavelength. The frequency, you know, it's measured in per second or hertz, but really it's how many times per second the waves are created, which means how many times per second the electrons are oscillating to produce the wave. I got to be careful here. It doesn't have to be electrons, it could be any charged particle. Take a piece of plastic and you charge it and you wave it back and forth, you're going to produce a very low frequency EMR. The other thing, before we get to a couple of examples, is if you look at the top of your screen here, the speed of light is the speed of all forms of EMR. When you look on your formula sheet and you locate the speed of light, which is here, first of all it says that's the speed of light in a vacuum. We'll learn later that the speed of light in air is a little bit smaller, but it would still be 3.00. It's so close that we just say it's the same number. So that's the speed of light in a vacuum. I wish, and I've asked a couple times, but nobody at Alberta Ed is biting, I wish they would change this to EMR. It's the speed of EMR in a vacuum. So if you're working on a problem that has microwaves in it, and you need to know how fast they're moving, that's how fast they're moving. How fast are radio waves moving through air or a vacuum? That fast. Any type of EMR. Let's try a couple questions. What's the wavelength and period of a 740 kilohertz radio wave? Most radios now, if you actually have a radio in your vehicle, it probably is digital. But I'm sure you're aware that radios used to have a dial and a little thing that would move along. And on the FM part of the band, it would say megahertz. It actually says that right on the radio. And on the AM band, it says kilohertz. So this is 740 on the AM band. This is CBC Edmonton, I think. And what that means is, in the antenna, that CBC Edmonton is using to broadcast their signals, electrons are dancing around back and forth, up and down, 740,000 times per second. The code, the language, the music, the words is encoded based on how far the electrons go. It's called amplitude modulation. So the electrons will oscillate a lot, and then they'll oscillate a little, and a lot, and a little, and medium amounts. and that's how we encode the signal. Well, I don't know much about it. All I know is the frequency is the same. If we want to find the wavelength, then we can use the universal wave equation of V equals F lambda. So we can put in the speed of the wave, 3.00 times 10 to the 8 meters per second. We can put in the frequency, 7.4 times 10 to the 5 hertz, and get the wavelength. Now, the wavelength will be meters because a hertz is a per second. So we're going to have to take 3 times 10 to the 8 meters per second divided by 7.4 times 10 to the 5 per second. And the seconds will cancel. If it's a math class that you want to focus on in your mind, I can multiply top and bottom by S. The seconds cancel and you're left with meters. If you don't want to think of it that way, we're dividing by a fraction, so you flip it over and the seconds go up top. The seconds cancel. So the answer here is going to be meters. I don't know what we're going to get. 3 over 7.5. So 3 times 10 to the 8 divided by 7.4 times 10 to the 5. So about 405 meters. That's mind-boggling. This electromagnetic wave from the peak of one electric field to the next peak of the same electric field is 4 football fields, the distance between those two peaks. It's huge. Very long wavelengths for radio waves. We still have to find the period. Let me write this down. Lambda equals 405 meters. The frequency can be used to find the period. The period is 1 over 740,000 per second. I'm not always going to write per second. I just want to make a point that those are the units and it works out properly. I will normally just write hertz. So you go 1 divided by that. (1.4 times 10 to the negative 6 seconds). Now, I mean, think about this. There's a lot going on here. Even though this is a lazy wave, very long wavelength, in other words, even though it corresponds to me tapping my foot in and out of the water not very rapidly, the electrons are going back and forth 740,000 times per second. And that's a low energy EM wave. Imagine how many times per second they would have to be going back and forth to produce something like an X-ray. Well, you know what? We don't have to imagine. Does anybody remember, what a typical X-ray wavelength is? Without looking. Your glasses. 10 to the negative 10. So, wavelength is 10 to the negative 10. We can calculate a typical frequency that would be for the frequency of X-rays. We would take the speed of light and divide by my typical wavelength. Correct me if I'm wrong. Three times 10 to the 18. Can you do that calculation? That's right. Pretty sure. So you can take the speed of light divided by that wavelength. the frequency that that electric field is changing at, or the magnetic field is changing at, is 3 million. I don't know how to describe that number. It's really rapid. That goes way beyond the beat to German thrash metal, right? It's incomprehensible what that frequency is. Let's look at one last question, and then we will be done for the day. The closest star, and we will actually learn in this class how we know how far stars are away from us. We can figure that out. Here, by just sitting on Earth and looking at a star, we can tell how far away it is using physics 30. The closest star to Earth is about 4 times 10 to the 16 meters away, that's a pretty big distance, right? How long does it take the light from that star to reach us? In other words, how long does it take light to travel that distance? So this time what we're going to do is just use speed equals distance over time. We can put in the speed of light. And the time, or the distance, is 4 times 10 to the 16 meters. When you take speed equals distance over time and rearrange it for time, you get time equals distance over speed. So we have to take that distance divided by that speed and get what I believe is going to be 1.3 repeating times 10 to the 8 seconds. Now, and that's the answer to the question. If we're not very intellectually curious, we can just end it there. But let's talk about that number a bit. I don't know about you, but if somebody told me, right? Paul, meet me back here a little later. Oh, when? In 1.33 times 10 to the 8 seconds. I would kind of be knocked on my heels a little bit because I don't know how long that is. So my immediate reaction would be to figure out how many minutes that is. And maybe I got a better handle on how many minutes it is. So I can take that number and divide by 60 because there's 60 seconds in a minute. And that's not really that helpful either. I mean, I can kind of wrap my head around that number a little bit more than the previous one, but I still I don't have a human experience for that length of time. So I can divide by 60 again, and what I'm looking at now when I do that is how many hours. And now I'm going, okay, well, I got time to go get a coffee before I come back and meet this guy, right? It's going to be a while. But I know that's a long time, right? So I'm going to divide by 24. So this is how many days. Well, okay. Now it's starting to take form in my head about exactly how long this is, because I know there's 365 days in a year. So if I divide by 365, and we're not going to worry about leap years, and somebody would say, well, 365.25. It doesn't matter for my discussion. I discovered that the answer to this question is 4.2 years. So when I look out at that star, I think it's called Alpha Centauri, and I see that light, that light that's hitting the back of my eyeball and forming that image in my head, that light that just entered my eye left that star 4.2 years ago. So I'm not really seeing that star as it is. I'm seeing it as it was 4.2 years ago. How many of you have heard of a light year? Yeah, a light year is not a length of time. A light year is a length of distance. And what we would say is this distance from Earth to that star, this 4 times 10 to the 16 meters, it's 4.2 light years. That's the distance. And when you consider that there are some stars and things in our universe that are billions of light years away, this is why astronomers get really excited. They're studying the universe as it was billions of years ago and millions of years ago. We're not looking at the way things are now. We're looking at the way they were before. Now, we don't have to worry about that. If I say what time it is, you're not going to take into account the time it takes the light to go from the clock to your eyes, right? Because it happens so quickly. Anyway, that's the last example. Any questions with that calculation or this question? All right, you have some calculations on the next page dealing with the universal wave equation, speed equals distance over time, those types of things. I'm going to hand back your exams again, but I'm not going to go through each of the questions that I didn't get to in the seminar this morning. I'm not going to do that now. I'm just going to give them to you, and if you need help with them, let me know. But I want you to work on these problems. Give me a minute to get settled in with something, and then I'll help you out.